Good evening, and welcome to my Aerospace 2220 lecture on aerospace controls for the first creative assignment for dynamics. Sorry. So, today I'm going to be talking a little bit about what controls theory is and kind of why it's relevant to dynamics. So, the reason why I'm talking about this today is because controls is a direct application of rigid body dynamics, although there's a couple steps between rigid body dynamics and controls theory. So basically, controls theory is a system of techniques to manage the conformance of a dynamical system to a desired state. That's kind of a complicated sentence. What does it mean? So first, I think a good way to start with it is give an example. So I'm sure everyone who's watching this lecture has probably been in an automobile before. So you guys might know what cruise control is. So cruise control is a system where your vehicle's rolling along the road. Whenever it gets a bit too fast, the engine slows down, it causes the vehicle to come back in speed. And when you go too slow, it increases the engine speed and you speed up. So basically, it keeps you up at this given engine speed by varying the engine RPM. So controls theory is the formal way of mathematically quantifying what that engine speed has to be in order to achieve and maintain a certain speed given disturbances such as maybe going up and down a hill. In this case, a more interesting application of that is adaptive cruise control. So in aerospace, controls is usually used for aircraft and spacecraft attitude and velocity management. So a lot of good examples are fly-by-wire for aircraft. So for a lot of airplanes, you have traditionally what you do is you have a stick which is mechanically connected to bell cranks, rods, and pulleys to directly actuate the control surfaces. However, in large airplanes, that's very difficult to do because the control forces are so high. So what is done a lot of times is the control stick directly goes to a actuator or a sensor in the stick or in the floor, and then that sensor data is sent to a flight computer, which takes that data, recomputes it, and then applies control outputs to all the control surfaces to change the attitude. Basically, that allows the aircraft to add certain control laws to protect the pilot from putting the airplane in a dangerous situation. Airbus is very well known for doing this. In addition, launch vehicles with thrust vectoring systems or quadcopters often take advantage of controls to manage their attitude. So there's two big types of control methods and loops that you'll see. Those are the closed loop and the open loop. So closed loop depends on the state of the system. So basically what that looks like is if you have a rocket or something flying through the air, whenever a gust hits the rocket, it goes off course. A closed loop control system takes data from that sensor, applies the controls application, like it moves a thrust vector or some fins or something, changes the state of the system, and then uses the sensor to check how well it did, see what input is required again, and then apply another input until you're back on your course, until you're at that desired state. And then it'll maintain that desired state. So for an open loop control system, the control input does not depend on the system. It usually follows a predetermined schedule of desired control points. So for example, washing machine. You set a wash time and you hit start. Basically, it just runs for a certain amount of time and it doesn't sense how wet or how clean the clothes are. It just runs to that time and then stops. So that's much simpler, but there's a certain amount of adaptability that you're missing. So there's a couple big control laws which take advantage of these techniques, which I'd like to talk about. So the first one is bang-bang control. It's the simplest type of control law. Basically, the idea is you use two commands, which is essentially like on and off to manage the state of the system. So for example, air conditioning usually works by turning an air conditioning system on and off to manage the temperature at a certain point. It's not very precise a lot of times. It's not very stable, but if you have a lot of natural damping, like for example the air in a room, or maybe fluid flowing a rocket engine under higher pressure, it's a system that you can use successfully. So the other control law, which is very common, is the proportional integral derivative technique, or PID for short. It's something you see in basically every aerospace control system, especially closed loop control systems. So it's most common for servo control, so like a servo motor like you would use for an RC airplane. Basically, what this law does is it takes the input data and then it runs it through this algorithm to determine the response that the control mechanism has to apply to get the system back to the desired state. So there's three terms that are used in this system: proportional, derivative, and integral. So the proportional term basically just tunes the output to be correct, to be proportional to the error. So if the error is large, the correction is large. If the error is low, then the correction is small. So the derivative term is added to that if the proportional term isn't good enough on its own. Basically, if say you have the system that's not as well damped, like a launch vehicle, and it's a little bit twitchy, if you have only the proportional control, it'll wobble around, it'll oscillate. So the derivative basically tunes that output so it's dependent on the rate of change of the error. So that gets rid of the oscillation. And if those two aren't good enough by themselves, the integral term is added to account for cumulative small error, and basically adds a extra refinement. So there's two big control theories that we talk about. So one is the classic control theory, which is basically one system input, one output. That's useful for simple systems like fluid control through a single pipe. However, in aerospace, what's more common is the modern control theory, where basically you can take a lot of inputs and outputs that are related to each other, which is what you do whenever you have an aerospace vehicle flying independently. So for example, this lander diagram that I have, a lander has an engine that is capable of vectoring in two different directions and can move in three and rotate in two other dimensions, actually three other dimensions. So basically, a modern controls theory approach takes into account every single one of those dimensions and directions that the thruster can gimbal, as well as the thrust of the thruster, and is able to model those and then have a combined input from the engine to manage a state in all 6 positional variables. So on top of that, another basic concept I'd like to talk about is the linear versus the non-linear system. So the linear system follows two main rules: homogeneity and additivity. So a linear system basically is a very predictable, very ideal system where the response varies linearly with the input, and two inputs that you give are the same as a single larger input. A nonlinear system does not follow those rules and is in fact more realistic. A linear system is an approximation that we can use to more easily find the controls behavior of a system. So one other technique that can be used is data-driven control. So that's something that is adaptable to the conditions, which allows for damage or failure resilience, but that's a very cutting-edge technique, which is a current focus of controls research. So another kind of way to do that, and another more advanced way to do controls, is reinforcement learning. So basically, that's quote-unquote AI controls. So you use machine learning to determine the best response of a system in a certain scenario. There's a couple different ways to do that, such as Markov decision process, which uses potential scenarios, and then whenever the system picks a good potential scenario, then it receives a reward, and basically that incentivizes picking the correct future scenario. So Q-learning uses a objective function, which is written to represent the incentive given for a specific response. You usually use machine learning to solve for how to correctly approach this problem. Speaking of which, there's a couple of optimization methods you can use that are based off of machine learning. So those are gradient-based systems and non-gradient-based systems, where you use a derivative field or an objective function to find an ideal solution to a certain situation. So one big application that I just want to talk a little bit more about is that gimbal thrust launch vehicle. So this is a very common aerospace guidance and control problem, and it's basically you have a rocket with a gimbal thruster, like with your lander, but you have to deal with aerodynamic stability at the same time. So basically that's done mechanically by actuating thruster controls using hydraulic actuators or something else, and executing roll control with some other method. That's required because launch vehicles are often not aerodynamically stable. In fact, they're usually actively aerodynamically unstable. So this is a very complex problem which accounts for a variety of factors, such as the corrective force being based on thrust, as well as changes in mass and moments from the center of mass changing continually due to the shift in the center of mass. So with all that said, hopefully this is a okay introduction to controls theory. Thank you for watching and have a good night.